What's up, people? Welcome to the session. How's everyone doing? I hope that all of you guys are doing good and taking care of yourself. Welcome to the session, people. My name is Anup and this is Vedantu. And today is the day that we are going to starting about sound. We're going to do the entire chapter of sound from the very basic to the the what to say the what is natural vibration, damped vibration, forced vibration, what is loudness, pitch, quality. All of that is what we're going to study today. So buckle up because it's going to be a long ride. We have a lot to do. So make sure that you have your pens and papers with you guys because I'll be asking a couple of questions in between. I want you guys to solve those questions. There'll be a couple of problems, not too many problems per se, because you don't have much what to say problems coming from this chapter, but there's a lot of theory that you need to understand from this chapter. So make sure that you take your pens and paper, note down everything that is important, all the formula that you need to remember, and also try to solve some questions with me, right? So without wasting any more of our available time, let's begin one shot of sound without wasting any time, people. Let's go with a simple quote for today, and so that we can start our day with a positive note. The quote is this: a positive attitude gives you power over your circumstances instead of your circumstances having power over you. Very true, guys. Very, very true. It does not matter. There's this is one thing that I always think of when I look at all these kind of quotes. Generally when it rains, birds take shelter under a tree. That's what birds do. Like when it rains heavily, they take shelter because you get your wings wet. What to say? You might not be able to get the same flight as you want. But then eagles, on the same hand, the same problem, but eagles fly over the clouds. So that's it, guys. It's not about what problem is in front of you, it's about how you deal with those problems. What is the way that you look at those problems and what is your attitude towards it? That is what helps you to, be one step better, right? So that's it, guys. Let's begin today's session. So sound waves, echo, natural force and damped vibration, what is resonance, and loudness, pitch, and quality of sound is what we'll talk about. So let's begin. Sound waves. Alright, now, first thing is that sound is a mechanical wave. Sound is a mechanical wave. That means that you need a medium for the propagation of sound. Sound can travel through solids, liquids, and gases, but it cannot propagate in vacuum because there's no particles over there. So sound is a mechanical wave, right? Now there are two types of waves. There are two types of mechanical waves also. You have longitudinal waves and then you have transverse waves. Now, longitudinal waves are those in which the propagation of the wave and the particles are both moving in the same direction. In other words, they are parallel to each other. The particles as well as the propagational wave, both of them are moving in the same direction. That is longitudinal wave. Transverse wave, on the other hand, are those where the particles and the propagational wave is perpendicular to each other. They're not parallel, but they're perpendicular to each other. So it so happens that the wave particles might be moving up and down, or the particles might be moving up and down, but then the propagational wave is towards the front. In those kind of waves, those are called as transverse waves. So basically this is what it looks like. So you see this, these are the particles. You see the particles and the propagational wave are both in the same exact direction, and that is longitudinal wave. Whereas transverse wave, on the other hand, you can see this, the particles are going up and down, but then you can see that the wave itself is moving this way to the front, and this way you see that they're both perpendicular or at 90 degrees to each other, and that is what is your transverse wave. So to tell you one of the most basic questions of your ICSE 10th, this is the difference between longitudinal wave and transverse wave. So longitudinal waves are those in which the particle, the vibration of the medium particles is along the propagation of the wave. Examples are sound waves in air as well as in liquids. Whereas if we talk inside the liquid, whereas if we talk about transverse wave, it is basically the vibration of the particles and the propagation wave is perpendicular to each other, and this is something that you see in solids as well as surface of the liquids. The surface of the liquids you are able to see transverse wave, Whereas magnitude or longitudinal wave is something that you see in the air as well as in solids and inside liquids as well, right? So that is the first thing, people. I hope you guys have taken a note of it. It's a very important question, so make sure that you take a note of this or download the notes because you'll get the PDF as well. So download the notes and keep this with you, right? That's it. Let's move on. Now, a wave has four important things: amplitude, time period, frequency, and wavelength. Let me tell you what that is first. Amplitude is nothing but the maximum displacement of the wave from its mean position. From this position, what is the maximum displacement? That is what is called as the amplitude. Time period is the time taken to complete one oscillation or to complete one full vibration. What is the time taken? That is what is called as the time period. Frequency is the number of waves that is passing through a particular point in 1 second time. In 1 second, how many, or if you take a particular fixed point, how many number of waves are passing through that particular point in a certain duration? That is what is called as your frequency. Wavelength is nothing but the distance between two consecutive crests or two consecutive troughs. This is what is called as your wavelength, which is represented by the Greek letter lambda, right? So these are the four things you have to understand. Now, this formula that I'm going to talk about is very important. So make sure that you note this down in your notebooks. Very important. Listen up carefully. The relationship between frequency, the wavelength, and the velocity of sound or the speed of sound in a particular medium is given by the velocity of sound or the speed of sound is equal to the frequency of the particular wave into the wavelength of that particular wave. So this is the relationship between what? The frequency, the wavelength, and the velocity of the sound, wave velocity and the velocity of the medium, or velocity of sound in that particular medium. So velocity is equal to V is equal to what? F into lambda. And the next relationship is the relationship between frequency and the time period. So if we talk about frequency, guys, frequency is basically inversely proportional to the time period. If time period increases, then the frequency is going to decrease. If frequency increases, then time period is going to be time period is going to be less. Because what is time period? It's nothing but the time taken to complete one vibration or one oscillation. Whereas frequency, on the other hand, not oscillation. Yeah, wow, we can say one full wave. One wave is what is called as time period. Frequency is the number of waves that is passing through a particular point. So if there are if the frequency is more, that means the time period is going to be way lesser, and as frequency is less. So basically, this is what the wave would look like. So imagine this is what it is. So this is when you have very high frequency, and this is something that you can say that is of less frequency. So you see this clearly when the frequency is more, you see that the time period is going to be less, because you see this to complete one full wave, it takes much lesser time. Here on the other hand, because the frequency is less, you can see that the time period to complete that same vibration or to complete the same vibration is going to be much more longer. Now, what is the velocity of a longitudinal wave in a gaseous medium? What's the formula for that? The formula is this, guys. Now again, you will not be asked any problems based on these formulas, but then you might be asked to put down the formula, and you might be asked to define what are the terms. All right, so there's not going to be any problems based on this, but it's still very important because they'll ask you to write down the formula to find out the velocity of light, velocity of sound in or velocity of longitudinal wave in a gaseous medium. So in that case, V is equal to root of delta P by D is the formula. So what is it? V is equal to root of delta P by D is the formula, where delta is the specific heat or ratio of specific heat. Now again, this is a concept that you will be studying in your higher grades. So delta is basically something called as Cp by Cv, that is the specific heat at constant pressure divided by the specific heat at constant volume. But again, you'll be studying about this later. But just remember this one thing, guys. For air, the value of specific heat is 1.4. So you just need to remember this one value. That's also specific heat for air for a particular medium is going to be same. So for air it's 1.4, and P is nothing but the pressure, and D is nothing but the density of the medium. So pressure, density, and the ratio of specific heats, which would give you what is the velocity of the longitudinal wave in gaseous medium. On the other hand, if you want to find out the longitude, so yeah, one thing that I forgot to tell you is this, people. So here it's again, the relationship is that if the density is less, that means the temperature and humidity is more. It's indirectly proportional, right? So the density is less, that means the temperature and the humidity is more. If that is more, if that means that the velocity of sound is going to be much more greater. So in other words, density is indirectly proportional to the velocity of sound. So just remember this, guys. If density is less, that means the temperature and humidity is more, and the speed of sound is going to be more if the temperature and humidity is more, because obviously density is going to be less if the humidity or temperature increases, right? So remember that it's indirectly proportional. And what is the factor that density depends on? Density depends on the temperature and humidity of that particular medium. Now, on the other hand, if we talk about the speed of transverse wave in a stretched string, if you have a string and you want to find out what is the speed of a transverse wave on that string, the formula goes like this: V is equal to root of T by M, where T is nothing but the tension on that particular cable and M is nothing but mass per unit volume. It is not the mass, it is not just mass, it is mass per unit volume. That is what is your, in other words, it's the lateral mass. You can see that it's the lateral length or lateral mass. That is what it is. So mass per unit length and tension will give you, the root of that would give you what is the velocity of transverse wave in that of a stretching. Now again, I'm going to repeat this. You will not be asked any sort of problems from this, but still it's very important to understand, because they might ask you as a 1 mark question or 2 mark question. They might ask you to define what is transverse wave, and they might ask you to put down the formula. So it's still important, but then again, you don't have to practice a lot of problems and stuff. Just need to remember this one simple formula, right? So these are the two formulas. We'll have few more formulas, but these are the first two that we'll start off with. Again, the longitude, if you talk about longitudinal wave, in the case of a gaseous medium, it's V is equal to root of delta P by D. On the other hand, if you talk about transverse wave, in that of a stretched string, it is the root of T by M, where T is nothing but the tension and M is mass per unit length. Right, okay. Now, I know that for all those who have not attended the previous session, you will still have this question: sir, what is the difference between light and sound? Why is it so different, and what is so different about it? See guys, light is an electromagnetic wave. It's an electromagnetic wave. Whereas sound, on the other hand, is a mechanical wave. And since light is an electromagnetic wave, it does not need a medium. It can travel in vacuum, so it can travel through pretty much any medium. It does not need a medium at all. Alright, even in vacuum it can travel. But then sound, on the other hand, because it's a mechanical wave, it needs the particles to vibrate, and that is what propagates the sound. So without the particles, it cannot travel. The speed of sound is speed of light is 3 to 10 to the power of 8 meter per second, whereas sound, on the other hand, is 330 meter per second in air. Now again, it differs with the temperature, humidity and all of that, but yes, generally we take it as 330 or 340 meter per second is what we take. Wavelength of light wave is very small. It's about 10 to the power minus 6 meters, whereas wavelength of sound wave is between 10 to the power minus 2 and 10 meters. So it's a little bigger. I mean, the wavelength is much more bigger in comparison to what to say, when you compare it to light, the wavelength of sound is much more bigger. And finally guys, light is a transverse wave, whereas sound, on the other hand, is transverse and longitudinal as well. So I told you this. If you talk about transverse, if you talk about the surface of water and even inside solids, you can see that it's a longitudinal wave. Sorry, it's a transverse wave. Whereas if you talk about longitudinal, it's generally in air, in solids and underwater. You see longitudinal wave. So you can see both type of waves in sound waves, but in light wave, light is always a transverse wave, right? Always. I know this sound is very irritating, it's distracting me a lot. I understand, but what can I do? It's not my car, someone else's car, it's screaming from that time. Alright, so people, here's the question. Compressions are the regions where the density is low pressure. Density is low, pressure is high. Density is low, pressure is high. Density is high, pressure is low. Density and pressure both are high, or density and pressure both are low. When you talk about compressions, so we have compressions and rarefactions. That is how sound waves travel. So what about compressions? Compressions are a region where density and pressure both are higher. That is where you see compression is happening, and rarefactions are those where the density and pressure is comparatively lesser. So compression, expansion, compression, expansion. That expansion is what is called as a rarefaction. That's all right. Okay, second one. In longitudinal wave, how does the particle of medium vibrate compared to the direction of propagation of wave? In longitudinal waves, How does the particle of the medium vibrate compared to the direction of propagation of wave? Is it perpendicular, parallel, or at 45 degrees or at 50 degrees? If it's longitudinal, then it's going to be parallel. If it's transverse, then it's going to be perpendicular. So no doubt is the answer is going to be option number B. All right. Okay, now since we've established few things which is common about both sound and light and few differences as well, let me ask you this question. Can sound reflect? What do you think? Does it? I mean, light reflects, we all know that. But what about sound? Yes. Just like light, people, sound can also reflect. So if there's an opaque object, or if there's a medium, it could be a wall, it could be a metal sheet, whatever it is. If there is a sound, if there's something blocking the path of sound, it will get reflected back, or reflection of sound wave would definitely happen. Just like how light does it. So light, you call that as the incident ray, and the light ray that gets reflected back is called as the reflected ray, and there's an angle formed in between the normal and the incident ray, which is called as the angle of incidence, and between the reflected ray and the normal is called as the angle of refraction or reflection, right? So here also you have the exact same thing. You have a medium light, that is called, so the sound is, that is the incident sound wave, and the one that gets reflected back is the reflected sound wave. Now here, once again, remember this, guys. In the case of light, for you to see that reflection, for you to see an image, you need a perfectly smooth, shiny surface. That is where you see that all the rays of light which comes in incidence on the surface, after reflection, they are all parallel to each other. They're all parallel to each other. The reflected rays are all parallel to each other. Whereas, if you see, if it's a irregular surface like a table or something like that, in that case what you see is diffused reflection. You see that the light rays would get reflected back in different directions, and again the problem is that you don't really you don't see any image as such. But then yeah, the reflection does happen, but it's the intensity is going to be less, the brightness is going to be less. But you will not be able to see the reflection of the image of that particular object, and that is what you see in light. But if you talk about sound, people, you don't need the surface to be smooth or rough. It does not really matter. If it's a smooth surface, yes, the intensity is going to be high, the loudness is going to be higher, it's going to be more clearer. So that kind of reflection is called a specular reflection. Whereas if you have a irregular surface, that kind of reflection that you see is called as a diffused reflection or diffuse reflection, which nothing but scattering of sound waves happening because the surface is irregular. But then again, here the amplitude might be less, which means the loudness is going to be less, but it does not really matter much. Like in the case of light, you need the surface should be perfectly smooth and shiny in order for you to see the reflection. But in the case of sound, that is not really needed. You can still hear that particular sound. Alright? Now, here's the thing, guys. Based on reflection of sound, you have to understand one more important phenomenon called as echo. What is echo basically? Echo is nothing but reflection of sound. In simple words, it's nothing but reflection of sound. But reflection of sound in such a way that you are able to hear the same sound not once, but at least twice. That is what is called as echo. So why? Why echo? What is the reason for echo to happen? And what are the conditions for echo to happen? And what is the formula to calculate the speed of sound if you talk about echo? So remember this, guys. Now remember, like let's say that you're shouting, right? You're standing over here and you're shouting out your someone's name, someone special's name. All right, you're standing on the top of a mountain. You're too happy, all right, and then because it's been so long that you've gone to school and stuff. So I understand, So you guys are shouting, all right. Now what happens is that the sound from your mouth, again, it'll travel, and it'll hit a surface. It could be a mountain, it could be anything for that matter, maybe a tall building or whatever, then gets reflected back. Alright, and then you are able to hear it once again. Now listen carefully, guys, listen carefully. The sound wave travels a distance d, right? That's what happens, it travels a distance d. Now, the same sound wave again travels back the same exact distance. So here the sound wave is traveling twice the distance, not once, but twice. Whatever the distance is, if it's 300 meter, 400 meter, whatever that distance is, it is traveling or covering that distance twice. It is going and then again coming back in the same particular, I mean, it is taking the same path in the sense it's covering the same distance, whatever is the distance between you and the building, it's covering the same distance again. So that is about echo, guys. The most important thing that you have to remember is that we know that speed is nothing but distance by time. But in the case of echo, because the sound wave is traveling twice the distance or is going back and forth, it will be 2d by t, because it is traveling back and forth. It is coinciding with the obstacle and then again getting reflected back and reaching back into your ears. And here V is nothing but the speed of the medium, speed of sound in that particular medium, and T is nothing but the time taken to cover that particular distance. So that is basically about echo, people. So if you want to find out the time taken is 2d by V, and if you want to find out the distance, D is equal to V into T divided by 2 would be the formula to find out the distance. So these are, again, rearrange the equation in order to get the same exact to get this from the same first equation. Now, you have to have at least two conditions in order to hear the echo. The first condition is this, guys. The sound that you hear should at least be spaced, or at least have a space of 0.1 seconds. You cannot hear the echo if the sound is heard right away. Echo is heard once so what happens is that your brain can't differentiate between the sound, because when you're talking, you can hear your sound, you can hear yourself. But when you talk about echo, that sound gets hit on the surface and gets reflected back and you're able to hear it again. So the difference, or you can say that the original sound that you make and the sound that you hear should have a difference of at least 0.1 second in order for you to hear the echo. So sound source should be long enough from the rigid obstacle so that you can hear the echo at least 0.1 seconds after the original sound. And in order to get that, the minimum distance that you should have is 17 meters. So how do we calculate it? It's very simple. Speed of sound in air is 340 meters per second. So we know that velocity of sound is equal to 2d by t is the formula. So you want to find out the distance. So distance is equal to v into t divided by 2. So v is nothing but 340 divided by 2 into 0.1, which is nothing but 17 meters. So at least 17-meter distance should be there between the person and the obstacle in order for you to hear the sound again, or in order for you to hear the echo, because only if that distance is maintained, only then you'll be able to hear the sound after 0.1 seconds, right? So these are the conditions in order for you to hear the echo. First one is that the minimum distance between the sound source and the obstacle should be 17 meters. The size of the reflector should be much more bigger than the wavelength of sound as well. You cannot have you cannot have a tiny little box after 17 meters after if you keep a tiny box and expect to hear the echo. That will not happen, because in comparison to the wavelength, the obstacle should be much more bigger. It should be much more, the reflector or the obstacle should be much more bigger in comparison. And the intensity of sound also should be high enough so that you can hear it back. You cannot just talk feebly and expect to hear the echo. You have to talk loud in order to hear the echo, because only if you talk loud enough, then the intensity of sound, only because there's a lot of loss also happening. So yeah, intensity of sound should also be high enough for you to hear the echo. Alright guys, so these are the three things. And what are the use of echo? It is used in sound ranging and echo depth, using ultrasonic sounds in the case of submarines and boats and stuff like that. It is used in echolocation by bats and dolphins. It is used by fishermen in order to see where the fishes are. They use echo over there as well. And it is also used in sonar and echoes in medical field as well. Your your MRI scanners and all that, it's magnetic resonating magnetic resonance imaging. So that also they produce ultrasonic sound in order to see what is the functioning inside your body. So yes, it is used in medical fields as well. It is also used in your ultrasounds to check the growth of the fetus and all that. In order to do that as well, they use echo itself. Right? So that's it, people. That is the end of the first part of the topic. We'll do one more question. Then we'll get back into what is natural frequency, damped frequency, and force frequency and all of that. So natural vibration, force vibration, and damped vibration. Let's get into that. So let's solve this question quickly, people. A person is standing between two vertical cliffs, produces a sound. Two successive echoes are heard, 4 and 6 minutes. Calculate the distance between the cliff. Amazing question. So imagine that you're standing over here. There's one cliff over here. There's one cliff over here. you're standing in the middle and you're shouting out. One side you're able to hear it after 4 seconds, whereas the other you're able to hear it after 6 seconds. They're asking you to find out what is the distance between these two cliffs. Go ahead, guys. Your options are 1,600 meters, 720 meters, 960 meters, or 640 meters. All right. For the first one, guys, I want to calculate what is the distance between the person and the first cliff. All right. So here the speed of sound is given as the velocity of sound is given as 320 meters per second, and time taken is 4 seconds. So first of all, calculate the formulas. D is equal to V into T divided by 2. So 320 divided by 4 divided by 2, 2 2s are 4, 4, and 3 to 6, 640 meters is the distance. For the second one, again calculate this velocity of sound remains the same, but time taken is going to be 6 seconds over here. So D is equal to 320 into 6 divided by 2. 2 3s are 6, so 0, 3, 3 to 6, 3 3s are 9, so 960 is what you're going to get. So what is the distance between the two cliffs? So add up both the distance. So D1 plus D2 is equal to the distance, that is 960 plus 640, which is equal to 1,600 meters or 1.6 kilometers. So that is the answer, 1,600 meters. I hope you got it right. Make sure that you guys have gotten this, please, people, because it's a very important problem. These are the kind of questions that you can expect from this chapter. Very simple, very straightforward. Just use the formula and get the answer. Alright guys, let's take a 1 second break. Are you guys enjoying the session? If you are, do not forget to hit the like button. Do not forget to subscribe to the channel. And if you want to attend more such amazing sessions with amazing set of teachers, click on the link that is given in the description as well as in the pinned comment section. If you want to join us, gain 100% knowledge, learn in depth about each and every topic, and score 100% marks as well, link is given in the description. So let me tell you what are the advantages of joining or being a part of Vedanta. Firstly, guys, you do not have any limits on how many number of sessions you take. You have unlimited live sessions. How many ever sessions you want, you can attend so many. With that, all of these sessions are going to be fun filled, and more importantly, every single questions or every single sessions will have unlimited number of quizzes as well. Lots and lots of quizzes which will help you to understand the topic and at the same time have a lot of fun as well. And though these quizzes, guys, will also help you to compete with the rest of the world and see how good you are at a particular chapter. You don't have to go anywhere looking for anything. All of the support will be given over here itself. So with the help of these quizzes, you can actually compete with your with your friends and see how good you are at this particular chapter. And if in case you miss out a session, don't worry. You can again take those quizzes during the replay sessions and also check out the leaderboards as well. So you want to take the quizzes 3 times, 4 times with the same session, same chapter, and make yourself better. Go ahead, people. Nobody's going to stop you. You can take the quiz how many ever number of times you want, even while watching the recordings, and still get the leaderboards for those quizzes. With this, people, added to this, you have all the opportunity to download every single premium content of all the session and the handwritten note of every single master teacher, every single session, all the recordings, everything is available to you at your fingertips. What more do you want? Every handwritten note, all the recordings, all the premium content, everything is downloadable and you can see it how many ever number of times you want. With this, guys, I would say this is the best part of Vedanta, that you don't have just one teacher to help you understand the concept. No. With the master teacher, you will also have the class teacher in order to clear every single doubt of yours. And the class teacher, no matter how many doubts you ask, 100, 200, does not matter. All of your doubts will be cleared inside the class itself, because they're there to help you guys out and make you guys, better every single day. And yes, people, for all of those who are looking for tests and assignments in order to make yourself better every single day, you don't have to go anywhere, people. You have quality tests and assignments, and these tests and assignments, the questions that are chosen are from your Olympiads, from your ISOs, from your past year question papers, from your sample papers. So from all of the mediums, the best of the best questions are what is chosen for you people, so that you can make yourself better every single day. So you don't have to go anywhere looking for anything. Everything's right here, and It's like a one-stop shop for your all educational needs. With this 5,000 plus micro courses and crash courses, like it's like a sprinkle on top of your ice cream. That's what it is. And yes, people, you're getting a lot more and for a lot less. The link is given in the description as well as in the pinned comment section. The coupon code is AME Pro to avail your discounts. Let me tell you what is the the price. Like if you go for the 1 month program, people, it's about 2,699. If you use the coupon code AME Pro, this is my coupon code. If you use that, you get a discount of 500 rupees flat, and the price drops down to 2,159. And if you go for the program where you have your classes going on until June 26 to June 21st, that means even after your exams are started, you know that your exams are starting from May 4th. Even after your exams are started, we'll be there for you people. So do not worry about anything, no matter what. Before the exam, after the exam, we are here for you guys to make sure that you guys are doing the best. And if you go for that program, people, if you use the coupon code, the base price of that is around 10,000 rupees. But if you use the coupon code AME Pro, you get a 3,000 rupees discount and the price drops down to 7,200 rupees. That means that per session, if you go for the 1 month program, you'd have attended roughly about 200 sessions. That means you're paying about 11 rupees per session. And if you go for the 4 months program, you're paying about 7.2 rupees per session. The link is given in the description as well as in the pinned comment section, and the price of each and every session, guys, is going to be less than what you pay for a packet of Lays, which lasts for 20 rupees, which lasts for 20 minutes at the most, right? So yeah, people, the link is given in the description. AME Pro is the coupon code. Let's check it out. With that said, people, let's get back to the topic. All right, one of the most important topics from this chapter: natural vibration, forced vibration, damped vibration. Now, I explained this very detailedly in the regular sessions. So if you haven't watched it already, go to the Umang series of sound. You'll find everything that is essential. But still, let's go through that. What is natural vibration? Natural vibration of a body is the periodic vibration where, in the absence of an external force, the body continues to vibrate. In other words, if I have a pendulum, right? The pendulum goes to and fro, right? If I do not push it, all right, or let's say that I give an initial push and it starts to go to and fro, that is the natural vibration of that body. So it's a periodic vibration in the absence of an external force. You're not giving any external force, you're not pushing it at all, it continues to do, or it continues to go to and fro. That is what's called as natural vibration. But the problem is, guys, natural vibration is not really possible on planet Earth. The reason is because there's air particles around you, so there's a lot of friction also, because when it's moving, when the bob is moving left and right, it experiences a lot of friction. So natural vibration is something that you can see only in vacuum, because the resistance should be zero, or you have to create a vacuum in order to create in order to make the resistance to be zero. And that is something which is that is needed in order for you to really understand what is the natural vibration of a body. Now, the period of vibration depends on two things. One is the size of the object and the shape of the object. Now, the time period is called as the natural period because that is the time taken for it to complete one vibration. And the frequency is called as the natural frequency of the body. So natural frequency is what? The frequency of a body, again, without the influence of any external force, that is what is called as natural frequency. And the time taken for it to complete the vibration is what is called as natural period. That's it. Examples can be a simple bob that is placed in its mean position. When you take it to the extreme position, it goes to and fro without any external force. That is the natural frequency of that particular body. Now, the formula to calculate natural frequency of a simple pendulum, again, you don't have to solve any questions based on this. There will be no questions asked, but it is still an important formula because they might ask you to just write down the formula, right? So the formula is very simple. It's the frequency of a simple pendulum. F is equal to 1 by 2 pi into root of G by L, where G is nothing but the acceleration to gravity, L is nothing but the length. If the length increases, frequency decreases. If the frequency increases, length, or you can say that the length decreases, then the frequency would increase. So, and it also depends on the acceleration to gravity. It also depends on the, this is how you find out the natural frequency of a body, or natural frequency of a simple pendulum can be found out using this particular formula. If you want to find out the natural frequency of a string, it'll be a little different, because over here, the first part of the formula is the same. F is equal to 1 by 2 pi is the same. But here you don't consider the length or the acceleration to gravity. Rather, you consider the spring constant and the mass of that particular body. The mass of the load is what you consider over here. So what is spring constant? Spring constant is something about which tells you how stiff the spring is. You know that some springs are very very stiff. You can't easily expand it. So that spring constant tells you how stiff the spring is. So that is one more. This is one more formula to find out the natural frequency of a spring. Now, here's the thing, guys. If you take a tuning fork, and hit it on a rubber pad, what will happen is that it'll start to vibrate. It'll start to vibrate with its own natural frequency. The same goes with even a flute also. There's air particles inside the flute, and when you blow it, the air particles will start to vibrate with its own natural frequency. And the formula is, that is, if you want to talk about the relationship between the length of the flute and the frequency, it's quite simple. F is indirectly proportional to L. So if length increases, then the frequency would decrease. The length is what? The length is nothing but the length of the air column, because the longer the longer the pipe, the longer the flute, more amount of air column would also be there. There'll be more air particles trapped in between as well. So yeah, frequency is indirectly proportional to the length of that particular air column. Now, every instrument, no matter which instrument you take, guys, tabla, mridangam, sitar, flute, harmonica, everything will all produce its own natural, they all have its own natural frequency. All right? And if you want to talk about the frequency produced by a string, the formula is going to be again different. Not the natural frequency, the frequency of a note, because you have different notes, like like for example guitar and all, you have different strings, right? Some of them are thin, some of them are thicker. So if you want to find out the frequency of those, the formula is F is equal to 1 by 2L. L is nothing but the length of the string, into the root of T by pi r square D. So R square is nothing but the radius, R is nothing but the radius of that particular string, D is nothing but the density of the material. So all of these are the factors that the frequency of a note in a string depends on. Probably notice that, in a guitar, when you hit one string, the sound produces different. When you hit another string, the sound produces different. And if you want to find out the frequency of that, this is the formula to do so. Again, there'll be no problems asked. Once again, I'm going to repeat this. No problems would be asked, but yes, you later still remember this formula, because they might ask you to write down the formula for this. All right. So what is the formula? F is equal to 1 by 2L into root of T, which is the tension on the string, divided by pi r square D. This is the formula, right? So what is it, people? And if you talk about natural frequency again, the nature of natural frequency is very simple, guys. The amplitude and the frequency is going to be the same, because in natural frequency there is no external force applied. So it's going to be the same. That is how the nature of the natural frequency is. But then the problem is this, guys. In our everyday life, we don't see natural frequency. What we truly see is damped frequency or damped vibration. What is damped vibration? Damped vibration is nothing but when there is an external force applied on it, where you start to see the decreasing amplitude, where you start to see that it starts to fade away. That is what is called as damped vibration. The periodic vibration of a body of decreasing amplitude in the presence of a resistive force of friction, that is what is called as damped amplitude. Like for example, if you take a pendulum, now if you start swinging the pendulum, after some time it will come to a state of rest. Why? Because the air particles, there is friction acting on it, and that kind of frequency, that kind of vibration is what is called as damped vibration. So in damped vibration, you have two forces acting. One is the restoring force, because obviously if you talk about a spring, your spring is always trying to come back to its original state. So there's a restoring force, that is called as the restoring force, because it always wants to come back to its mean position. And there is frictional force also acting. In the case of natural frequency, there is only restoring force acting. There is no frictional force. But here, with the restoring force, there is also frictional force acting on it. So you see the amplitude, it keeps on decreasing because of the friction. It keeps on decreasing, and eventually it will just fade away. That kind of frequencies, or that kind of vibration, is what is called as damped vibration. For all of those who are confused still about natural and damped vibration, these are the difference between, guys. Amplitude of natural vibration remains constant and it continues forever. There's no stop because there's no friction in an ideal case. In the case of damped vibration, it will gradually decrease with time and ultimately it will stop. There is no loss of energy. There is some loss of energy in the form of heat. No external forces acting on the body. Here there is external force acting on the body, and like I told you, it's only restoring force acting on it. Here restoring force and frictional force acting on it, and the frequency of vibration depends on the shape and size of the body. Here the frequency depends on the like frequency is always going to be less than the natural frequency, obviously, because it's decreasing. It's not going to be the same. It's going to keep on decreasing until it completely fades away. Right, guys? So let us now get into the last type of vibration, which is nothing but forced vibration. Forced vibration is very simple. The vibration that takes place under the influence of an external force is what is called as forced vibration. When there's continuous force given, for example, when you talk about a microphone, there's a diaphragm inside the microphone which keeps on vibrating. So what do? When you talk, the air particles vibrate and the diaphragm also starts to vibrate. So when you're giving an external force, you're continuously giving an external force to it. So that kind of vibration or that kind of vibration that happens in a body under the influence of an external force, that is what is called as forced vibration, because you're not letting the microphone to come to a state of rest. You're continuously speaking, and every time you talk, the diaphragm starts to vibrate and it starts to produce the sound. So that kind of vibration is what's called as forced vibration. Now there are three forces acting in forced vibration. One is a restoring force, because obviously every body will come back to its will try to come back to its original state. Frictional force, because of the air resistance. And an external periodic force as well, because that force is continuously making the body to vibrate. These are the three factors that forced vibration depends on. Now again, the amplitude, the type of wave of the force vibration depends on you. It depends on the external force. What type of external force is it? If the external force keeps on increasing, then the amplitude will also keep on increasing. If you have the external force where you're stopping it for a second and then again starting it, that time the wave would look a lot different. So that is how when you talk about force vibration, it's a lot different, because it's up to the external force. You have no control. It's the external force that decides what type of vibration it is. So to talk about the difference between natural and forced vibration, natural vibration, in the absence of an external force, here there is an external force acting on it. Here it depends on the size and the shape of the medium. It depends on the external force applied. The frequency is constant over here. The frequency keeps on changing depending on the external force. The amplitude of vibration remains constant. Again, depends on the external force. So everything about this depends on the external force itself. Answer this question. When a body vibrates with its natural frequency, the force acting on it is zero, proportional to its velocity, proportional to its displacement, or a constant force. When a body is vibrating with its natural frequency, the force acting on the body is going to be proportional to the displacement, not the velocity. It's not zero, it's not a constant force also, it's proportional to the displacement. So the natural frequency, obviously when you talk about natural frequency, it will displace according to it, whatever the natural frequency is, whatever the natural frequency of the body is, it will displace according to that itself. So it's going to be proportional to the displacement, nothing else. Next one. In the damped vibrations are with amplitude decreasing with time, amplitude increasing with time, constant amplitude, first decreasing amplitude, then increasing amplitude. The answer, option A, people. In damped vibration, the amplitude keeps on decreasing. It does not increase, it keeps on decreasing. Right? Alright, people. Okay. One of the most important concepts. We have two more topics left, that's all. I know, I told you, it's a long topic. We have a lot to do, so let's finish this off as well. What is resonance? See guys, every body, not everybody, every body, every object has its own natural frequency. Now, when the forced frequency or the forced vibration becomes equal to the natural frequency of the body, once again, listen carefully, when an external force or the forced vibration is equal, or the frequency of the forced vibration becomes equal to the frequency of the body, the natural frequency of the body, what you notice is that suddenly the amplitude of vibration will increase, or it will start to vibrate with a much higher amplitude. That type of frequency or that type of vibration is what is called as resonance. Once again, people, look at this glass. This glass has its own natural frequency. Look at the waves that you see. Those are the sound waves that is coming from let's say there's a speaker. Alright. when the frequency of that forced vibration becomes equal to the frequency of the natural frequency of the glass. Look at the glass carefully. You see that the glass are vibrating. The size, you see the glass, it's vibrating. It starts to vibrate with greater amplitude. That is what is called as a resonance. And the frequency at which this happens is called as resonating frequency of the body, or resonant frequency of that particular body. So resonance is it's a special case of forced vibration where the vibration is induced and that vibration becomes equal to the natural frequency, or the frequency of the the forced vibration is equal to the frequency of the natural vibration of the body, and that is when you see resonance. All right. Now there are lots and lots of examples that helps you to understand resonance. For example, look at this. There are two tuning forks. Both of them have the same frequency. Both of them are the same. You have to make sure that they're both of the same frequency. All right. Now see this. When you hit the first one, the other one starts to vibrate. Why? Here's what happens. When this starts to vibrate, it will start to vibrate with its own natural frequency. And that will start to vibrate the air particles below. That will vibrate the box. The box will vibrate the air particles below. So the air particles is also vibrating with its own natural frequency. It will go over here. It will vibrate these air particles. And what happens is that this tuning fork also starts, because these boom box starts to vibrate, or the sound box starts to vibrate. You see that even this fork, the tuning fork, also starts to vibrate with the same frequency as that of this one. But then when you change the tuning fork, you see this suddenly when you change the tuning fork, when the frequency changes, that time you don't see anything. So when you talk about resonance, both the bodies, or in this case, you should understand that the frequency should be the same. So this is the forced vibration over here, and this is the one that is vibrating with the natural frequency. And when they both match, the amplitude increases, and that is what you see over here. They both start to resonate. The same goes over here also. You have 5 pendulums over here. So you see this. When you move this pendulum, the vibrations travels through these string. It will travel through this one, it will travel to this one, it will travel to this one, it will travel to this one as well. But when you see this, only this one starts to move with greater amplitude. Why? Because the frequency of this one and the frequency, they're both of the same length, and because they're both of the same length, they'll have the same frequency, and you see that they will both start to vibrate at a similar frequency. They both start to vibrate at a similar frequency, and the amplitude of the third one would be much more longer or much more bigger in comparison to all the three. This is also one more example of resonance, right? So this is the forced vibration, this is the one creating the forced vibration, and the natural frequency is the same. So you see that both of them start to vibrate with the same frequency, and the amplitude also increases. So this is one more example, guys. Again, the notes will be given to you, so don't worry about it. One more example is the resistance in air column also. So if you take a tuning fork, again, keep it near a column of water. This will start to vibrate. The air particles, the water particles start to vibrate. They'll vibrate these water particles inside, and again this will also start to vibrate. And you suddenly hear a loud sound on the other end. Why? Because the sound produced, or the vibration of the fork that is creating the forced vibration, is equal to the natural frequency of the water particles. So because of that, or the air particles, you can see that the air particles also vibrate with the same frequency, and when they do that, you're able to, suddenly the amplitude increases and you're able to hear a loud sound, right? So then the natural frequency of the air column becomes equal to the frequency of the fork. You're able to see a loud sound, and that is again what is called as resonance, right? Yeah, guys, I know. I can only wonder what you guys are doing sitting over there, but still, we have to do what we're here to do. So examples of resonance, guys. Resonant, if you talk about resonance in pendulum, we just saw that in machine parts also. Like for example, if you have an old car or an old bike, when it starts to vibrate, everything starts to vibrate. The whole, like only when the engine is the one that vibrates, but then the entire body starts to vibrate, because once it reaches the natural frequency, and it'll start to vibrate more violently. That is something that you see. Resonance in stretch string, resonance in air column and tuning fork, resonance in the case of bridge. This is mostly called as aeroelastic flutter, but still you can it's more sometimes you'll probably see that when the wind blows heavily, the bridges start to move left and right. Again, that is also because the forced vibration, that is nothing but the air particles which is creating which is the forced vibration, the frequency of that would be equal to the frequency of the bridge, and that is when you start to see that. But then This is actually called as aeroelastic flutter. Aeroelastic flutter. Alright, it's a different phenomena. It's not because of resonance, but there's a common misconception. So it's okay. Finally, guys, we also have resonance in TVs and radios. How does your TV and radio work? You have to tune into that particular frequency, 94.5. Why 94.5? Because when you tune into 94.5, the frequency that is coming, that is already coming, that is getting transmitted from those big transmitters, when the vibration of that will be equal to the natural frequency of the, so you're adjusting the natural frequency of the radio, right? So when it becomes equal to the natural frequency, or the frequency of the force vibration will be equal to the natural frequency, you start to see that it will start to produce the same sound, right? Again, the difference between is given over here, people. You can download it, don't worry about it. So force vibration under an external periodic force, and again, the frequency, natural frequency is different from the force frequency. In resonance, the external periodic force and the frequency of the external periodic force and the natural frequency is the same. Amplitude is smaller, amplitude is very large over here. In this, the vibration of the body is, it's not in phase with the, it's not like, it does not happen at the same time. Here they are both in phase, and here the vibration lasts for a small time because of, the periodic, because of the external force, it will start to, it will cease to stop after some time. But here, on the other hand, it will last for a much more longer time because it is vibrating with a natural frequency, right? So yeah, one more question. This is the one. Resonance occurs when the frequency of the applied force is exactly half the natural frequency of the body, exactly equal to the natural frequency of the vibrating body, twice the value of the natural frequency, or any value greater than the natural frequency. And the answer is option number B. Exactly the same as the natural frequency of the vibrating body, people. With that said, finally, the last topic is the characteristics of sound. Loudness, pitch, and quality. What is loudness, pitch, and quality? Let me tell you this on an overview. Loudness tells you how loud, how loud or how soft a sound is. Pitch tells you how shrill or how, how much, bass do you have in the sound. And quality tells you, both loudness and pitch are the same. Quality is basically something which tells you which instrument is producing that sound. Okay, let me explain that. Like I told you guys, loudness is a characteristic which tells you how loud the sound is. So you can distinguish or differentiate between a loud sound from a faint one, a loud sound from a faint one, using this, what is called as loudness. And loudness is something which depends on the amplitude of the wave. You see this? This shows that the loudness is less. This has less loudness or a soft sound. This, on the other hand, is a much more louder sound, because why? The amplitude is more. In fact, if you talk about the relationship, loudness is proportional to the square of the amplitude. So loudness is proportional to the square of the amplitude. So if amplitude increases by a factor of 4, then loudness will increase by a factor of 16. That is what it means. If amplitude increases by a factor of 2, let's say, then the loudness is going to be increase by a factor of 4. So it's square of that. And loudness is also inversely proportional to the square of the distance. It's inversely proportional to the distance, the square of the distance of the source. So as you go further and further away, the loudness will also increase. Loudness depends on the surface area as well. That is why you see this you see that a bigger speaker will produce much more louder sound compared to a smaller speaker, because the surface area is more. So air particles that are in contact with the bigger surface will be more, so sound will be much more louder. It also depends on the density of the medium, and also depends on a resonating body. If there is a resonant body, then the loudness would also increase, because again, the body would start to vibrate with the same natural frequency. The frequency would be the same, and the amplitude increases, so loudness would also be more. Pitch, on the other hand, tells you the difference between a shrill sound from a grave one. Like for example, think about it. A girl's voice is very sharp, whereas a man's voice is much more deeper. So how do you differentiate that? That is with the help of pitch. And pitch is something which depends on the frequency. Higher the frequency, higher the pitch. Lower the frequency, lower the pitch. Higher the frequency, higher the pitch. Lower the frequency, lower the pitch. On the other hand, people, so remember this, for man, the pitch is generally a low pitch voice. Men have a low pitch voice, whereas women, on the other hand, have a higher pitched voice. That is why it's very sharp. You can clearly hear the sound much more sharply. It's much more sharper in the case of women, but in men, on the other hand, it's much more deeper, right? You have much more bass. So that is nothing but your low pitched voice. Finally, if you talk about quality or timbre, if both the loudness and pitch is same, how do you differentiate the sound? Let's say that there are two instruments, guitar and let's say a piano. Let's say that both of them have the same loudness and same pitch. So how do you differentiate which is coming from a piano or which is coming from a guitar? You differentiate that with the help of quality or timbre, which is nothing but the waveform, because each and every instrument has its own type of waveform. This is what is called the waveform. You see this in a flute, the waveform is a lot different. In a voice of a person, the waveform is different. So that difference is how this is how you tell the sound produced by a flute or a guitar. You can differentiate that sound with the same loudness and same pitch by using this one quality or this one property of sound, which is nothing but timbre or quality. That's it, guys. So that is the last thing. Yeah, these are all the things. Depends on the amplitude, frequency, and waveform. Loud sound from a faint one, shrill from a grey one. If the same loudness and pitch, how do you differentiate the sound with the help of quality or timbre, right? The last question, guys. Here we go. That's it. I am done. I will not bore you people anymore. Here's the last one. What is the difference between a low pitch and a high pitch sound? Is it low pitch sound has a higher frequency and high pitch sound, and then low pitch sound? High pitch sound has a larger frequency, a larger amplitude. Low pitch sound has a larger amplitude. Both sounds have the same frequency and say different amplitudes. The answer, guys, is I think option number A should be the right answer. High pitch sound has higher frequency than a low pitch sound. So yes, that is the answer, guys. And yeah, one more question. Loudness and softness of sound depends on what? The speed of the wave, the wavelength of the wave, the amplitude of the wave, or the time period. Loudness and softness depends on the amplitude. The greater the amplitude, the loudness is going to be more. Lesser the amplitude, it's going to be a softer sound. And that completes the topic for today, people. The whole chapter, what we took, I believe 5 to 6 sessions we completed in 1 hour. The link is given in the description if you want to take a part, if you want to join us. Coupon code is AMEPRO to avail the discounts. And okay, people, that is all from my side. Do not forget to hit the like button. That was a lot of effort from my side as well. Do not leave without hitting the like button. Do not forget to subscribe to the channel as well. I'll see you guys in the next one. Until the next time we meet, this is Arnav signing off for the day. Have a great evening ahead, people. I'll see you guys soon. Take care of yourself. Stay safe.